Okay, hi, welcome to another video in which we will be discussing the combination of the two-dimensional diffusion and the two-dimensional uh, convection equations. So, to start with, let's have a look at the equations. So, the two-dimensional convection and diffusion combined. On the left-hand side, we see the time derivative term and the convection terms and the diffusive terms. And here we have a similar kind of that equation for the v momentum as well. So some superscripts and descriptions of variables. The solution algorithm is simply we pass the old vector values and we subtract the convection to which the diffusion term is added. And this time we will try to implement some fixed value boundary conditions as well. Compared to everything else that we have done before, we didn't have any boundary conditions, only some initial conditions. Okay, so first things first, let's go ahead to CodeLight and we will create some boundaries, starting with giving some names. Let's say we call a string inlet, which will be known as capital all caps inlet, a string outlet with simple letters outlet, to which we will call this as outlet, and a right side to which we will call as right, and a string left side which we will call as the left. Right, so let's go to, we will implement this as a function in fields class. So let's write a function, say that this function is void function, which is called fixed value boundary, and it can take any two-dimensional vector field and a string and a double. So what are these? Let's have a look. So we put this guy here and some curly brackets to describe, and we will call this prescribed value, call this name of the boundary, and this will be simply vec, and say that this belongs to the fields class, so it can be only called through an object of fields. Right, so let's start. If name is equal to inlet, then let's have a look at I'll just quickly draw something here. I have already discussed this geometry, nevertheless right, so remember what we discussed about I direction and J direction. So I is going down by rows, so basically this is where the top one is, let's say that this is the left hand side, this is the inlet, and this is the outlet, and this is the right hand side, and I starts from here and I ends here, so I is equal to nx minus 1, and j starts from here, so let's put this guy here, say that j equals 0. Let's put a simple j, actually j equals 0 and j equal nj or ny minus 1, and let's put an arrow to indicate the direction. So here we go for the jth direction, Right, so now everything is a bit more clear, at least I hope. And therefore inlet is here, this is the inlet, and it goes from all the way to I equals 0 to I equal nx minus 1. So for int I equal to 0 to I is less than vec dot size, and then I plus plus, and then j will be equal to vec. So let's say int j will be equal to vec dot size minus 1. Yeah, and therefore now we can prescribe a value. So if we are in that boundary, then the value will be equal to the prescribed value. And similarly, we can do this now a couple of more times. So copy this entire thing, and I don't know why it is not copying. Okay, so else if name is equal to outlet, then j will be equal to 0 because that's where j starts, and the value will be 0.0. Else if the name is equal to right, then so right hand side is here where I is at the size, so I is equal to, so we need to change this now to j. We are iterating in j, but if we go all the way towards the end of the vector, there will be a corner node where I and j will share locations. So this time we want to be going to -1 and 1. So for the inlet, it will take from the start to the end, and for right and left, it will start from one node after and end at one node before the inlet. So simple as that. And here the I will be equal to vec dot size -1, and the last one, the left hand side, where if the name is equal to the left hand side, then I is equal to 0 because our left hand side is belongs to I equals 0, and therefore the value will be this. Else if else, let's just say else, hold on a second, seem to have done something. So this void should end extra bracket here. Yeah, so else cr that the boundary name, and then name, then this name comes from here, is not found in the geometry. So the geometry composes of only inlet, outlet, right and left. Of course, when grids get complicated, you could just create a series of names from the actual grid boundary names. Here I'm just using a very simple inlet, outlet, right and left, or east and west, or something like that. Okay, let's see if it will build. Says right, something extra which is not needed. Okay, so basically we want to remember our initial conditions, that the whole field is initialized to the value of 1.0, and somewhere in the middle there is a region with the value 2.0 for both u and v velocity. And now what we want to do is prescribe a value of 1.0 at the boundaries so they don't change throughout the simulation. Okay, so this will be useful for us. Right, so that is done, and we will implement this. We will actually call this function when we write the solution loop. So let's see what we have to do now. We have to write the convection equation plus diffusion part equation together. So uh, instead of writing it from scratch, I will go to this 2D convection that we did, go to edit, and just copy the equation from here until here, right, and paste it here. So we go convection equation, and I will just change the name to uconv diff equation, and here also vconv diff equation. Then I will put the entire convection term in a bracket for both u and v, and then add the diffusion term, which is simply fd Laplacian x of u plus fd Laplacian y of u multiplied by, so another bracket, solution dot viscosity multiplied by the entire thing, and close this bracket. So now we have written the diffusion term, and copy this guy here, delete some stuff, and change this to Laplacian of v velocity. So there we go, we combine them together now, and this time again we won't be calling through the solve method. We can easily write a solve method, but we will change this to a much simpler method, in which we will just say that the new velocity will be old minus solution dot dt multiplied by whatever is the outcome of this equation field, and then put this in a bracket. Okay, so there we have it. And similarly for v new also, we will say v new will be equal to v minus bracket solution dot delta t multiplied by vconv equation dot equation field. Right, so now it's time for us to implement the boundary conditions. So remember the object of the class fields, which was called field upper. So we can only call this function that we just wrote, fixed value boundary, through this object. So we will call field upper dot fixed value boundary, and it says you have to import three things: so vector to field 2D, a name, and a value. So I have already written that the b value is equal to 1.0, so this is the boundary value, and we will call this for u new inlet, which we wrote the name that we wrote here. Where was it? Yeah, inlet, outlet, all with simple letters. So inlet, and the value will be b value. Right, so let's build this and see what we have. Okay, so there we go. Now this is just for the inlet, and we have to copy this for everything else. So outlet, two more times for the u velocity, right and left, and copy the entire thing for the vnew. So we are implementing fixed value boundary condition, and the reason I did it through this method is because we might want to change at some point, for example, the outlet to be a zero gradient boundary instead of fixed value, or something else like if you implement the temperature equations, thermal, isothermal boundary, or adiabatic or something like that. So we have more freedom this way. Easily we could pass in a vector of strings for all the boundaries and just have this as a single function. But for now I think this should do. So let's compile. Okay, so that's done. Let's see how many grid elements. 20 by 20, 400, and delta t, viscosity 1e minus 3. So let's see if this, let's build again and go to the directory. Let's go to the directory, controls, and delete some old files. Oh yeah, and run again. We are running for 700 time steps. Let's run. Okay, brilliant, it's done. And we close this and we go to look for our visualization software, ParaView. For some reason I keep closing it every time, and that's not ideal. So let's wait for ParaView to open. Right, I think it's loading. Yeah, I can see it now. And we go and open. So there is a couple of files here which makes me slightly confused. Let me go to open, CodeLight, build debug, bin. Okay, so now we are in the right directory. Okay, let's see if things worked out as we planned. Okay, so it's perfect because we have this, let's put a rainbow. We have this velocity field in which we increase the velocity, and when we run it we see that it's convecting, and at the same time it is diffusing as well. So because the value is decreased to 1.3 maximum value, and at the beginning we have a value of 2.0, and it's propagating something like this. So it's spreading out, at the same time it's propagating as well. So we have the convection diffusion equation sorted now, and in the next lesson we will be doing the Laplace equation.